Hey guys, welcome back to another episode of the Real Hacker Hours podcast. Today I will be trying to write a new detection for a new type of bug within Linux, so the Ghidra static bug finder I've been working on these last 10 videos or so. And to illustrate it, this source code file here shows exactly what I'm trying to do. Effectively, I want to be able to detect potential integer overflows or underflows. And to show what I mean, here we go. Call the function von with -1 as an argument. Here, it will just scan an input into input, the size of the input, and then it will do comparison against this integer argument to verify that it's less than 100, and if it is, it will pass it as a size argument to memcopy. Now, why this is an issue is this comparison right here is a signed comparison, and since it is a -1, -1 is less than 100. However, the size parameter to memcopy is unsigned, and since it's -1 signed integer, the unsigned equivalent of it is a super large value, so it ends up doing a buffer overflow. And let me show you that in action right here. Run it, asks us to scan an input, and then it crashes. We're sure that the memcopy call is called because this puts call who of you will dare is printed, so that memcopy is indeed what is crashing it. And just to just make sure I'm not making a mistake here, I'm just going to recompile it with the size of 1. And yeah, that did not crash. Cool. So I want to write a check for that. Let me just recompile it. Oh, I need to input it? Yeah, okay, cool. So that binary has the type of bug I want to write an additional check for. Now, for how I plan on doing this, I'm right as of this time, I still need to figure out how to do it. How my initial thought of how to do this will be is we have the size parameter here, and we effectively will check to see is it used in comparisons before this, and if there is a comparison, can we somehow tell is it a signed or is it an unsigned check? And if it is a signed check, and we know that the argument 2 here is unsigned, we can mark that as potential integer overflow or underflow. So that's what I'm trying to do. That's how I think I can get it done. Let's see if it can actually work that way. I'm going to close out some of these tabs. Okay, let's first go ahead and just run Linux on this test binary. Okay, let's go ahead and run it. Specify the project directory and the project name. Specify the binary we are importing. And specify to run Linux. I spelled that. Okay, give this a second to run. As this runs, I'm gonna open up Ghidra, the actual GUI version, and throw the binary in here because I get the feeling that that might come in handy for doing this work. Tools, Ghidra. Oh wait, no, what am I doing? This is the wrong path. Linux test, basic, int 000. Okay, cool. So we have that there. Let's open it up in the GUI. Analyze it. So we can see here it does a comparison here. What I want to do is, okay, we might need the Ghidra GUI later, but for now I'm just going to close it. What I'm going to do as a basic first step is, okay, we can see that Phalanx runs successfully on the binary. I want to, what is the right term? I want to get the P code for the exact comparison of it, and then hopefully from there I can do something to tell if it is signed or an unsigned value. Okay, cool. Now that I'm back, so what are we going to have to do this? We're going to need to write our own new check for this. So let's go ahead and just make that. Public void int overflow. Let's go ahead, just take a second and just make the new check for that. Now for this check, we're probably going to have to do it a bit differently. Primary reason for that being, so all of their checks up until this point, you're really only looking at the P codes associated with the call itself. However, in this instance, we need to look at the previous P codes before that. So we're going to need to iterate through all of the P codes of the function, not just the P codes associated with the function call. So in order to do that, of course, we will need to have this code here. I should really stop copying pasting this code and just offload it to a helper function. And we will need to get the P codes from here. However, we aren't just getting them from a particular address, we're getting them for the entire function. And P code. We are going to iterate through all of the P codes of the function. For a start, I'm just going to have this check just print out all of the P codes of the function just to verify that we are indeed able to iterate through all of them. Okay. Current, I know, let's just print it out. Current P code. And I'm going to add just a constant string print here just to help it be easier to see it in the output. Okay, and now I'm going to add this check to the memcopy. Where is analyze memcopy? It's right here. Function to analyze and the reference. And let's go ahead and run this. We need to switch over from tag import to tag process since the binary has been imported. Okay, something went wrong. Tag process. Bad or, oh, I forgot the tag here. Okay, let's go ahead and run it. Let's see what happens. Okay, I made, as you can see here, a small typo. 989. Wait. Yeah, line up. Okay, right here. That should fix it. Okay, cool. So you can see that it printed it out. Now, let's see. Where does it make the call? Multi-equal, in add, load. Not equal, cast, C branch call. I'm pretty sure this is not. Get the feeling that these instructions here are the yeah, the stack canary check right there. So I'm pretty sure that's not what we're looking for. Indirect call. Yeah, I'm pretty sure this call right here is for the memcopy. Has the 3 arguments for memcopy, and we can also take this address and yeah, okay, cool. So this, where is it? This right here is the memcopy call. Now, source destination size being this register var node. Now the question is, where's the comparison? We know that looking at the vol function, the puts call precedes that, so we should be able to go up here and see another call. Pretty sure this right here is the call to puts. We can check it doing this. Yep, we can see here that is puts. So this is the call to puts. We see here there's a branch, or C branch. So we see here, I get the feeling that, okay, so with assembly code, a lot of the times it will do a comparison followed by a branch if this condition is right. This right here is a branch instruction, or branch P code, I should say. Pretty sure, and I'm pretty sure this right here is the actual conditional int sless. I'm just going to go ahead and just Google the P code. Okay, I'm looking at the Ghidra docs on another tab for int sless. This is a signed integer comparison operator. Okay, so this makes it easy. We can see here, so I'm just gonna bring this over here for a second. Looking at the docs, there's a P code for int less and int sless. The difference is int less is an unsigned integer comparison operator, and int sless is a signed integer comparison operator, which that's pretty pretty useful in our instance, since we could just check what is that operator there to determine what type of, if it is a signed integer or an unsigned integer operation. Cool, we figured that out. Now the question is, how can we then tell where or how, well, if this var node ends up in there? You see here, this var node is for register OX10.8. We see here that right here there's a P code. Not sure what this P code does. Actually, let me see if I can't look it up on the same. Okay, I'm right now reading what this P code right here does on the same Ghidra doc page that I pulled up the other day. Sign extend the data in input 0 and store the result in output. Copy all the data from input 0 for least significant positions of output file. Pending. Okay, the TLDR is it takes this value and stores it in here. So this is effectively where the data for the size is going to come from. Moving it here, we don't see either of them. We don't see either of them used. Well, that's a different register value. By the way, for the var nodes that are register, this second argument is an enum that actually specifies like which register it is. This last one just specifies the size in bytes of the register, I'm pretty sure. And when you look at this comparison, we see here that this register that then gets stored in the size here is used. Okay, cool. So what we can do, how I'm imagining this, is we effectively, how can we do this? I would imagine that we would have to iterate through all of the P codes, and what we can do is we can effectively just track, like, okay, this of our where var nodes get moved to and from, and then yeah, we trace where the var nodes end up, at least in terms of the registers. Make it simple at first, and then we, for comparisons like int s-less, we can check to see which of our nodes are used, and then we actually get to the memcopy call. We can take the actual source or the size of our node and check to see, since we have the chain of where the var nodes moved from, we can check to see, does any of the other var nodes that this value stems from be used in a signed comparison check, and if so, mark it as a bug. That was a mouthful, but let's get started. I'm going to pause this for just a second just to think of exactly how I want to implement this in the code. Okay, I think I've thought of a slightly better way to do this. I forgot when I was like trying to come up with a solution. Ghidra, the P codes, they keep track of the var nodes, they keep track of the P code in which they were defined. So what we will probably be able to do is to do the backwards tracing to see like where this value comes from. We can just call it like the get, or here. There is a function in here that I call a lot called like get def on a var node, and that will give us the P code in which it was defined from. And from there, we should be able to actually tell, like, okay, this is the value that is derived from it. And so we can tell that exactly where the var node, and just to keep doing that if the var node's back. Now, what we also would do, you'll still iterate through all of the P codes. However, we'll probably have like a hash set that on signed operators, we'll just keep track of, like, oh, hey, these var nodes were used in a signed comparison. So that way we can still track or tell, like, hey, this var node, which our size var node is derived from, was used in a signed comparison. So let's go ahead and do this. For this, there are effectively two things that we need to do: iterate through all the P codes and find out which var nodes are actually used in a signed comparison, and then do the backwards propagation from the size of var node, to see if any of the var nodes the size of var node is derived from was used in that signed comparison. Cool. So let's get at it. We iterate through all the P codes if current P code dot get opcode is equal to, what is the full Ghidra program model P code op. It's signed. Yeah, that. Okay, yeah, that is the correct. I just checked on the official docs. That is the correct P code name. And do a comparison. If that is that, we will. Is there an output for this? Okay, yeah, we see that the output is stored here, and then there's a C branch here which evaluates that output and then branches depending on that. What I want to do is I want to iterate through all of the var nodes for the signed comparison. Pretty sure this should be capital var node. So we iterate through all of it through the inputs, since the inputs to the comparison are what's actually being compared. Okay, let's just go ahead and print them out. Okay, cool. Sorry, I had to pause the video for a second. Cool. This should print out all of the var nodes for, and also let's comment out that line so you don't get all the P codes. This should print out all the var nodes for the comparison P code. Oh, it should be get inputs. Yeah, the get. So the Ghidra P code class has the get inputs method, which will return all of the input of var nodes, and the get input method, which takes a single argument, which will return like either the first, second, third, whatever argument. So you see here, there's a register and a constant. Cool. What I want to see, I'm right now in a different tab looking up on the Ghidra and Java API docs. For the var node, similar to how like the P codes have like a P code op type, I want to be able to get like look at what the type is for the var node, so I can tell, is this a constant, is this a register, like what is the value being compared here. Ghidra var node Java. Okay, let's see, is there like a get type, get size, get space, is input. There is a dot is register value and dot is unique. Pcode op, variable short, offset PC address, size, space, word offset. Yeah, I think looking at dot is register might be the way to go here. Let's also add that here. Next, we'll just print check just to see that. Now, I know logically speaking, we shouldn't have to do this calling that dot as register method. However, I just wanted to test out real quick just to make sure it works the way that it should, because this stuff doesn't always work out how you think. Okay, so we see that it just actually match it as a register. Now, one thing that we might want to do is instead of calling dot as register, we can call, what's the right term? We can instead check if it is a constant. Reason for that being is right now we're seeing that the comparison is a register against a constant. However, I'm not an expert in how Ghidra P code models all comparison, and I might do it as a unique or something else. So we can check if it is a constant, and if it is a constant, we effectively move on to the next one. And if it is not a constant, we just add it to the hash set of var nodes that are used in a signed comparison. So if v dot is constant, we continue. So if we get to this point, we should only have a var node inputs to the signed comparison that are not constant. Cool. Now, I also need a okay, now I should probably make the hash set for the var nodes. Hash set var node signed comparison var nodes equals new. So that is our hash set where we're going to store the var nodes, and we can just go ahead. Oh, I just realized I spelled it wrong. Dot. I think it's add. Might be. No, I'm pretty sure it's add, not put. Just going to go ahead and change this typo from seen to signed. Okay, let's go ahead and run it. Okay, it looked like it worked. I commented out the print statement, so not entirely sure. But let's just uncomment out the print statement just so we can check. Okay, cool. That looks like it worked. It printed out the var node, which happens after we add it to the hash set, so that should work. Now, where does that leave us? We need to... Okay, now we need... So, right after this check for if it is a signed comparison, I'm going to add the rest of the code to effectively check, hey, is this the actual call site? I just realized one potential issue with how I'm doing it. So I'm iterating from the first P code to the last P code. Now, issue with that is that will effectively trace and assume that it has a linear code flow. However, a lot of code flows, they just jump all around the place. So that will be a problem that I need to fix, but I'm not going to deal with that right now since one problem at a time. Okay, get this, get the address. Okay, so this code right here, if we get down here, we should actually get to the P code, which actually makes the call. Okay, let's run this. It should print out call time with the P code associated where the call is actually being made. Okay, yeah, that's right. This is the P code where the memcopy call is being made. We can tell that from the 3 arguments to memcopy. Cool, so... Okay, what do I want to do? Now, we tackled the problem, at least excluding the, all the code paths that jump around. We solved the problem of keeping track of which var nodes are used in the sign comparison. Now we need to solve the problem of doing the backwards propagation to see if the size var node, if the value is derived from any of those other var nodes. For that, what we can do is we need to get the size argument for this memcopy, which means that we will need to add in an argument for that, int size arg, and we'll need to change that here. It is the second one. So let's go ahead and first just implement into this check that we can get that var node. So that's the first problem that we need to solve here. The input to this should be for y4, 3 arguments from memcopy plus the input for the actual call instruction. And let's go ahead and put that here. And then we can get the var node size of var node equals inputs size arg plus 1. Oh wait, I also want to add a print statement so we can actually see the var node itself that we are getting. Okay, let's run this. Okay, cool. So we see that the var node that it got was indeed the size of our nodes. That is cool. We can see that that is good. Now, the next step I think it is, let's see if we can get where was the P code that was defined in. So, good news is we can see it is here. Now, okay, we can see that the P code that was defined that was here. So we could get the input to this and then check it if it's in the hash map and then report accordingly. Now, one thing, in this instance, since this is just a nice little POC, the first of our node that it got its value derived from was directly used in the sign comparison. Now, one thing that might happen is you might see that the var node that is actually used in the comparison versus the var node that was actually used in the size argument, that there might be multiple var node copies in between them. However, that's getting into a bit more of a complicated scenario, which right now we need to first get this working before we start worrying about like more of the complicated stuff. So what we can do is we can do pcode definition pcode equals size var node dot get def if definition pcode is equal to null. Continue. So if it gets to here, the P code should actually be valid that it returns. That's good. Now, where does that leave us? We need to actually iterate through the inputs to it. Or, how do we want to do this? I should probably write a better, like, get, because right now, typically how I typically try to get the value of things is I look at the P code that's defined and just iterate through the inputs. I should probably have logic that it's actually like, let's actually look at what type of P code operation is going on and then analyze the arguments accordingly. So, but for now, I'll do for var node v in definition P code dot get inputs. In that instance, we will, if signed comparison var nodes dot contains v, okay, let's see if this works. If it prints out signed bug, it detected it, and how it detected it. It looked at the definition P code where it was defined and iterated through all the inputs and just checked if any of those var nodes belonged in the signed comparison var nodes, which is a hash set which stores all of the var nodes where signed comparisons happen. P code. Okay, looks like I had an issue here. Oh, this should be a P code op, not just a P code. So let's see if this runs. Okay, sign bug. It called it. Cool. Now, I just want to actually. I think I know how I can do this. So I'm going to. So in this instance, it is able to actually detect it via signed bug. I don't have the like fancy print statement working right now, but I'm going to worry about that after I just verify that this POC is working. What I want to do is now I want to add a test case for effectively the negative or the counter of it to verify that it is indeed working the way I want it to. And for that, what I can do is I'll make another test case that's fairly similar to the first one, except I'll show you. I want to do differently. Effectively, I'm going to change this from a signed to an unsigned integer. By making an unsigned integer, this comparison here should compare this as an unsigned integer, and because it's an unsigned integer, -1 will be interpreted as a really large value, so this code in here should not run, and I'll add in a print statement and the else condition just to verify that that is not running. Okay, we're falling further down. So in this instance, since I established it is an unsigned integer and doing the comparison, there isn't a bug. So I'm going to go ahead and run FileNext against it and just verify that it is not actually detecting a signed bug there. Okay, I should not print out signed bug. And it did not. Okay, cool. So at least in a baby POC way, we have detection for like at least this instance of like signed, unsigned integer bugs. It will need a bit. I would like to have a bit more work in this area before I can I feel confident with it, like really like finding more bugs out in the wild like this. But this is a good starting area. The stream has been going on for 38 minutes, so I'm going to go ahead and end it here. Thank you for watching.